Okay, well, I guess now is a good time to start. So this is the first of, I hope, many meetings on stratified homotopy theory. And I just wanted to take a minute before we actually started with the mathematical content to explain how this is going to work, because I think this might be a little unusual. So there are at least two things that I think are unusual. The first thing that's unusual is that this isn't just a seminar. In fact, it's a working group, and I really want it to function as a working group. So what that means is that we're not really, I mean, I have stuff prepared here, obviously, but the goal isn't to give a talk. The goal is to have a conversation. So I hope and expect that you will interrupt me. And if you don't want to interrupt me, then the second thing that's unusual about this is that we have Peter here, Peter Hain, who's going to be playing the role of kind of a Greek chorus for this whole thing. And the way that will work is that he's going to ask questions and anticipate the kinds of things that you might be asking. But then in addition, he'll also be reading chats or whatever to see if you have brought up anything. And so, you know, Peter will be Peter's sort of interrupter in chief. Peter will be interrupting me frequently, I hope.
Well, yeah, I've never done this before, so this will also be a part of what's new.
There's several aspects of this that are experimental, but I thought it would be it'd be a fun way to do things. In particular, I really, you know, I don't want this to be sort of just me talking into a computer, because I think that well, it won't be as much fun for me. And plus, I want to know that I'm getting across some of these ideas. Let's see, Peter, what else should I have mentioned?
Harry says, I've interrupted people before, but it hasn't always been constructive.
Yeah, that's okay. You can still interrupt as long as you've. No, I've actually liked Harry's interruptions in the last seminar we gave. I think they were good interruptions, so I'm happy. Okay, so I guess we'll start, unless there's a question about the structure or anything like that.
What is the time frame that we're? Is this for a set amount of time, or?
No, it's not for a set amount of time at all. Okay. I really would like this to last
at least 7 hours.
Oh, you mean today?
Yes.
Well, we have 2 hours booked.
Okay.
You know, we can use as much or as little of that as possible. I mean, if everyone in the room is left except for me and Peter after 30 minutes, then that'll be a clear signal that it's time to wrap up. But we have 2 hours, and we have I don't know, 30 hours of material that we can chat about. But you know, so the material is always going to outlast the seminar. That's the whole, or the working group. That's the whole point.
Wonderful.
So yeah, I mean, I'm not going to have like a destination with the talk or anything like that. I'm just going to tell you some stuff about the way I think about these things. Other questions? Concerns, complaints? Well, then I guess I will begin. So the talk here is about stratified homotopy theory. And I think what I want to do to try and introduce the topic of stratified homotopy theory is I want to sort of conduct everything via an aphorism. And the aphorism that I want to work with here is that sheaves, perhaps some particular family of sheaves or some category of sheaves, determine the homotopy type. And in the other direction, that homotopy type will actually recover the sheaves. That's the little motto that we're going to be working with. So there are lots of ways in which this motto gets kind of played out in the real time. And so I'm just going to explore a couple of sort of simple examples of that. And we're going to kind of use this aphorism a few times. And then ultimately, we're going to use this aphorism to motivate our construction of the homotopy category of stratified spaces. So that's the destination. So there's the motto again. Sheaves determine the homotopy type, and the homotopy type is meant to recover the sheaves. So So to be a little more precise about what's going on here, X, this little green X here, is going to be some kind of geometric object. And I'm going to be quite agnostic about what kind of geometric object it can be. What's that? Did someone say something?
I think it was just a microphone issue.
Oh, okay, that's all right. Geometric object as in a topological space or a manifold or a scheme or whatever exotic thing that you want to think about. Any of these are going to be candidates for our X in time. And A of X, well, A of X is just going to be my shorthand for some infinity category that we like of sheaves. And again, I mean, the different kinds of categories that you choose are going to affect the kind of homotopy type that you output. So the sheaves are going to determine a homotopy type, which I'll call maybe pi A of X. And our friend pi A of X will then recover this category of sheaves. And that's how this whole structure is supposed to operate. So the way this will work is that you'll have this kind of balancing thing. If you have a lot of sheaves, if you give me a whole pile of sheaves, then you're going to get a very, very fine invariant. Your pi A is going to be a very fine invariant of your X. If you give me very few sheaves, then you can expect not to get such clear information. And you can sort of balance that out as you see fit. And so part of the whole program that we're talking about here is about balancing that out to something that's actually finer than a traditional homotopy type. And that's what we're heading for in the near term. So I want to give an example of this principle in action. Actually, maybe before I do that, maybe I want to do this. I want to say what I mean by the word recovers. I should say something about that. Because what on earth does recovers mean? Well, so recovers means that I've got this functor here. I've got this functor here that goes from X to A of X. It takes some kind of topological object or geometric object that you're interested in and extracts this class of sheaves from it. And what I want to do is I want to factor that. And I want to factor that through some sort of homotopy type. And I want to factor it in a particular way. I want to factor it in such a way that this functor here becomes fully faithful. And that's the kind of structure that I really want to get after. I want to be able to factor this thing, but at the best level possible, I want to be able to factor it in such a way that this functor here becomes fully faithful. So that in fact, the information of the sheaves is exactly the same as the information of this homotopy type pi A of X. That's the goal that I'm trying to get to. All right. So I'm going to call this functor, this fully faithful functor of mine, I'm going to call this functor rep A. Now, again, I'm not going to really say what I mean by rep A, except to say that it's going to be, so we'll be agnostic about what rep A means. But often enough, we'll have rep A will actually be some kind of functors from your input homotopy type to A of a point. So part of the point here is that actually has a meaning. So for us, homotopy types are going to be things that are not only are they going to be things that exhibit some piece of the geometry of the thing, but they're also going to be things with the property that you can say what it means to map out of them as a functor. And so this is the kind of correspondence that we're going to want in the sequel.
So did you name this rep A because sometimes it's some category of representations?
Indeed, I did. So the one key example that's going to be playing a big role for us is the situation in which pi is actually, say, the fundamental group or fundamental groupoid of a space. And we're actually going to be talking about literal representations of that group or groupoid. That's actually what we're going to be doing in reality. Other questions? Okay, so this is the general setup. Let's see a little bit more. So the in these cases, what are we doing? Well, we're really representing this functor, the functor that carries x to a of x. And so what does that mean? That means that we're trying to exhibit an object. Let me sort of try and highlight where the object is. We're going to try and find an object here that solves this representability problem. That's actually going to be our goal. And we're going to do that for all different kinds of sheaves. Okay, but enough sort of general wittering. Now it's time for examples. Let's go. So here's the first example. Let's take the extreme case. So the extreme case is that we're going to look at a of x, and x is going to be all sheaves on x. And actually, for the moment, I'm just going to be talking about all sheaves of sets on x. So x is going to be just a general topological space. I'm not going to try to narrow my class of topological spaces at all right now. I'm just going to work with a topological space. And this funny symbol here, what's this? This is the category of sheaves of sets on x. On our friend, the green X. Now you might be wondering what this is all about, this less than or equal to 0, and that's just for later, because sooner or later I'm going to have to generalize to sheaves of more exotic things than sets, because, you know, as homotopy theorists, we're going to have to think about such things. And so I have this kind of symbol here in place. And so what's the question? The question is, if I take, yes.
So your x tilde will be sheaves of spaces on x, and then x tilde less than or equal to 0 will be sheaves of 0 truncated spaces or sets.
That's right, exactly. Yeah. So these could be called, if you felt like being clever, 0 truncated spaces. So somehow one of the things that happens after you become a homotopy theorist is that you start referring to all the objects that you knew and loved as an ordinary mathematician as if they were sort of the exotic things, and then the default things are the things that were all homotopy coherent and generalized. So it's like you're an alien on a planet that never saw the category of sets. You only saw the infinity category of spaces. I don't know. Is that just me?
No, it's me too.
Oh, good. Peter's an alien too.
That's also familiar to me.
I knew Aaron was an alien.
You really mean a discrete ring?
Yeah, exactly.
Yeah.
Okay, so I'm going to give a definition here of a particular class of topological spaces that are very good from the point of view of this category of sheaves. And this is the category of all sheaves. And so what is this class of spaces? This is the class of sober topological spaces. And just one sec while I take a sip of bourbon. Good. X is a sober topological space if every irreducible closed subset, Z, contains a unique generic point. Okay, so what does that mean? What that means is that when you look at the map that carries X to the closure of X, it's a bijection. And what's it a bijection from and to? It's a bijection from X to the set of irreducible closeds in X, which I'll just denote by IX. Irred closeds in X. Okay, so does everybody know what an irreducible closed is? Okay, I saw Phil shaking his head now, good. So an irreducible closed is a closed that cannot be written as the union of two smaller closed subsets. So if you're used to Hausdorff spaces, those aren't very exciting. There aren't so many irreducible closed subsets. But if you think about the world of schemes and stuff, they're all over the place. And so what we require is that we have special points, and there's exactly one for every irreducible closed, such that its closure is exactly that subset. I've just realized that I don't ever start a talk without yammering about general topology for a little while. I don't know what's happened to me. I never used to do this. Anyway. All right, so let me give you some examples. Well, so the first example is that if X is Hausdorff, then it's a sober space. And the reason for that is that the only irreducible closed subsets are just points. And Hausdorff spaces are in particular T1, and in T1 spaces, points are closed. So this is a nice sober space. Okay, so that's telling you that, that you can start to think of sober spaces as a kind of separation condition. It's not one of the, what's the word, Trennungsaxioma. It's not one of the T's because it doesn't compare well with T1. So in fact, the way it works is that any sober space is T0, and any Hausdorff space is sober, and any Hausdorff space is T1, and any T1 space is T0, but these two can't be compared. So it's just somewhere in there. It's T1 prime or something. Okay, let me give another example here. So another example is that if P here is a poset, and this will be an example that haunts us for the rest of the semester, so we might as well get comfortable with it now. We're going to give this, if we have a poset, we can always give it a topology, which is called the Alexandrov topology. Maybe I'll write that down. Well, I can only write it down if I can fit it. Let's try that again. Alexandrov topology. In which a subset is closed if and only if it's a sieve. So what does that mean? Well, that means that it's going to be closed if and only if for any P and Q in our P, if P is less than Q, but Q is in Z, then P is in Z as well. So it's sort of, what's the phrase, downwardly closed subsets. Is that what you were going to say, Peter?
Yeah, that is exactly what I was going to say.
Okay, good. So closed means downwardly closed. And that's the Alexandrov topology. And now you could clearly have made the opposite condition, but that's just going to confuse matters. So we'll always do it this way. We'll always have the closed things be downwardly closed. That's just the rule for the rest of the semester. Otherwise, I'll get confused. Okay, so this isn't always.
Can I ask a silly question?
Yeah, of course.
Motivated by that? Is there a name for those topological spaces where you can define a new topology by declaring the closed to be open? And then that satisfies the condition of being a topology. Oh yeah, because that's an example. This is an example of that.
Yeah, and it's actually the only example of that. So
wonderful.
Yeah, so these things are called, you could call them finitely generated topological spaces. So they're the same things as, so if you look at the, let me just make sure I'm saying this correctly. So here are the facts. First of all, a finite topological space is always of this form. It's always a poset with this Alexandrov topology. That's fact number one.
Oh, can't it be a pre-order? Like you can have two points
right,
that
yeah.
are
Thank you, Peter.
In discrete topology. So yeah, but this prescription makes sense for a pre-order as well.
Yeah,
so when you're allowed,
what's a pre-order?
It's the situation in which if X is less than or equal to Y and Y is less than or equal to X, it doesn't necessarily imply that the two are equal.
Oh, that's weird.
They're the categories that are equivalent to posets.
Yeah. So,
yeah. The
question: won't it then fail to be sober because it fails to be T0?
That's right. It will fail to be sober then. It will certainly fail to be sober. That's right. So so let me correct myself. Thank you, Peter. So the finite T0 topological spaces are the same things as posets. And the finite topological spaces, finite posets, and the finite topological spaces are the same things as pre-orders with the Alexandrov topology. Those are always the same as well. Now, to get to Aaron's question, so you can look at that class of topological spaces, and then you can try to detect your opens using that class of topological spaces in the same way that you do with compactly generated topological spaces. So I have a topological space, and I'm going to look at a subset U, and I'm going to say that U is, I'll just make this term up, finitely open, if and only if, for every map from a finite topological space in, the inverse image of that thing is open. It's the same thing I do for compactly generated topological spaces. And those guys have the property that you're describing. They're exactly the same things as topological spaces with the property that the closeds are closed under arbitrary union, for example. And so, and those are the same things precisely as pre-orders in general and posets if they happen to be T0.
Wonderful. Thank you. That's great.
Good. Any other questions? Okay, so now in general, this is not going to be sober. This is, even if it is a poset, it's not going to necessarily be sober because you can write down really goofy posets if you're willing to be infinite. But if you're willing to be finite, then all those problems go away. So if P is finite, then in fact, this topology on P is sober. And let's see why. Well, let's suppose that I have, if Z in P is an irreducible closed, then it's going to be of the following form. It's going to be of the form P less than or equal to Q. And what do I mean by that? Well, that's going to be the set of all elements P in our poset such that P is less than or equal to Q. But that in turn is the same thing as the closure of Q inside this poset topology, the Alexandrov topology. And so that precisely means what we want it to mean. It means that in fact we're talking about a sober topological space. Okay. So the next example, by the way, maybe just to emphasize, oh yeah.
Yeah, so if I want to, if I've not thought of this before and I want to start thinking about these things, can you describe some stuff about when the poset is the most simple poset 0 is less than 1?
I can. So let's do that. I'll erase this and put it back in a second. Yeah, so let's see. So let's consider that possibility. So P could be 0, 1, where 0 is less than 1. And well, what happens here? So, well, everything is open and closed, and the empty set is open and closed. So I just have to tell you which of the singletons is open and which one is closed. And so the singleton 1 by itself is open, and the singleton 0 by itself is closed. And so this is often called the Sierpinski space in textbooks. It's one of those early examples of topological spaces. But it's actually kind of an interesting example in a lot of ways. So for example, if you take a map from, if you've got a topological space X and you take a continuous map from X to 0, 1 with this topology, maybe I'll emphasize that I'm taking the Alexandrov topology here. Well, then what does this do? This exactly classifies for you an open set of X. Right, to any one of these continuous maps, I can look at the inverse image of 1, and that will be an open set. And if I happen to have an open set, then I can write down a map that says, if it's inside the open set, go to 1, and if it's not, don't do that. And that's a bijection, so that maps, continuous maps from X into 0, 1 with the Alexandrov topology are the same things as open sets of X. Of course, they're also the same things as closed sets of X. So.
Could we also see an example of an infinite poset failing to be sober? I think there's like a minimal example, one which is not down finite. Spec Z, after all. I believe.
Let's see. You're saying that if I take a, so let's see if I can do that. Right. You're asking me to do something cool. And I'll try to do something cool. So let's see here. So you're saying, so let's see. So give an example of one that isn't finite. And you're saying that if I do something like take this as my sort of maximal point, and then have a bunch of points mapping to it.
Right, just countably many. I think this will be the minimal.
So this is a countably many. And you're saying that in that case, it's not a sober space.
I guess so, yeah.
I think this is still a sober space. Am I mistaken? So let's look at what the closed are. So the closed are everything, right? Those are closed.
Yes.
And each of the points is closed. So I think this is still sober.
Oh yeah, okay. So that is not a minimal example.
Yeah.
Yeah.
And relatedly, your condition was not if and only if.
Oh yeah, it's definitely not if and only if. Very far from.
Even about down finiteness, though.
I don't think
Go ahead,
so.
Harry.
Oh, I was going to say, I think that the example is going to have some sort of infinite chain in it, and like at least that. So.
Yeah. There's this is a half remembered example, so forgive me if this is wrong, but I happen to remember an example that kind of flows like this.
Oh, yeah, that was the one that Jonas showed us, right?
Yeah, it's that example is something weird.
I think this one isn't sober, although if you press me on that, I'm not going to be able to produce for you a proof. I believe that this one is not sober. And if you like what I'll do is I'll go away and think about this and then give you a correct proof that it's not. I just don't know off the top of my head. But yeah, I believe something like that can be done where it's not sober. This is the right example, isn't it, Peter?
Yeah, I think so. I mean, yeah, certainly this is the example where sheaves on it fail to be hypercomplete, and that like all the weird stuff happens.
Yeah, I feel like this is kind of a universal counterexample for some of this kind of stuff.
Yeah.
So I think this one's not sober. I'll go away and think about it just so I don't make too much of a fool of myself. Let me come back to that. Is that okay?
Yeah, totally. I don't want to sidetrack us too much.
Well, no, I mean, I think that, as you know, I mean, finite posets are going to be okay for a lot of what we have to do. But as soon as you start thinking about the kind of stuff you've been thinking about, like Ron spaces and so forth, you have to start accepting infinite posets. And and as soon as you do, I think some of the kinds of theorems that I want they just need extra hypotheses. So it's probably a good practice for us to know what those extra hypotheses are. But anyway, that'll come later. We're anticipating too much of the future, maybe. Okay, so let me just say this. So
did you want to give your XR thing that I made you erase?
Oh, yeah, thank you. Thanks, Peter. Right, so I have another example of a sober topological space. So why don't I say it? Right, good. Another example of a sober topological space. So if I take a scheme X, then I'm entitled to take the Zariski topological space that underlies it. And that Zariski topological space is always a sober space.
Oh, so my example was doomed to fail. Yeah.
What's that?
The counterexample I was trying to give was doomed to fail. It was spectral.
Well, so the example so it's actually quite interesting. The example that you gave isn't the same thing as an XZAR quite. There's a subtle difference. So sorry, I shouldn't give you credit for it because I drew the picture, not you. But when I drew this picture as a post-it, so just to say, I mean, when you look at say spec Z with the Zariski topology, that's a pro-finite poset, but it's not an infinite poset.
Right.
Right. It doesn't have this property, for example, that the closeds are stable under arbitrary union.
Yeah, there are two different topologies there.
There are two different topologies.
Right.
And
Okay.
so
Yeah, I take that
yeah.
back.
So you can your guy is the Alexandrophification of the usual Zariski topology, but even the usual Zariski topology is still sober. That's what I want to say. Yeah. So that's another good stockpile of sober topological spaces. Okay. So here's a fact. So if you have a sober topological space, well, then the points are the same things as the irreducible closeds, right? They're bijection with a canonical bijection with one another. And so that means that if you understood the lattice of opens, then you'd also understand the lattice of closeds. And irreducibility for a closed is something that can be determined from the lattice. So that means that you can reconstruct a sober topological space from this lattice of open sets, right? That just happens. So information that you get about X is the same thing as information that you can get from this lattice omega X. So in particular, we're going to start thinking about sheaves, and sheaves are, of course, just certain kinds of functors on this lattice of open sets here. And it turns out the category of sheaves will be sufficient to reconstruct the lattice, which will then be enough to reconstruct X itself. So a corollary of this is that X can even be reconstructed from this category X tilde less than or equal to 0. You can actually explicitly reconstruct it just from there. Okay, so that means that as soon as you know, if you have a sober topological space, as soon as you know its category of sheaves, you know the topological space itself as a set and everything, like up to homeomorphism, you know that thing. Now, the other fact is that if you're not sober, excuse me for 1 sec while I pour some bourbon. If you're not sober, then you can always sober up.
I was waiting for that pun to show up.
Yeah, me too.
So you can always sober it up. And how does the sobering up process work? The sobering up process says, well, take your X, look at the irreducible closeds of your X. Those things admit a topology. And the topology is basically the one that is universal with a map from X itself. Right? So there's always a map here. There's always a map here from X to I of X, which is given to you by carrying X to the closure of X. Right? And you could just give this thing the universal topology with respect to this map. And if you do that, then you end up with a topological space, and you end up with a sober topological space. Notice that this thing need not be either bigger or smaller. Notice that this I of X here need not be either bigger or smaller than this X. Right? Because, for example, if you're not T0 and you have 2 points that are topologically indistinguishable, then they'll become the same inside I of X. And then if you've got some subset where you don't, an irreducible subset where you don't have a generic point at all, then you'll have to introduce one. So you might make it bigger and you might make it smaller. Both things can happen. Okay, so this is actually a left adjoint. To the forgetful functor.
Jan has a question.
What's up?
Jan has a question.
Fire away, Jan.
It says, does
me
this
see.
have the quotient topology?
Yeah, it has the, well, it's whatever, it's is it initial or final, do I say, topology with respect to this map?
So the map is not, as you said, it's not surjective.
It's not, needn't be surjective, right?
Yeah, it need not be surjective, but it's kind of what the definition of quotient topology, except that you don't.
That's right. Yeah, exactly. Yeah, you take a subset is open if and only if its inverse image is open inside X. Yeah.
Thanks.
And what you show, by the way, it's a fun exercise if you've never done this before. And if you like general topology, it's fun. And what you show is you show that that the irreducible closed of Ix actually agree in a one-to-one correspondence with the irreducible closed of X. And then that's how you show that this thing is really fixing up your X in the right way. I like your cat, Phil. Okay, so we have a topological space X. We're trying to consider all sheaves, right? We're trying to think about all the sheaves on X. Now, all the sheaves on X are sufficient to reconstruct the lattice of opens of X, but that's only enough to reconstruct the sobrification of X, this I of X here. So I think some people call this the sobrification. Is that the right word? Does anybody know?
I think so, but
Peter thinks
it's a reasonable name.
Peter likes
Yeah, it seems fine to me.
I'm not sure if it's the most common one, but anyway, that's the thing. So what does that mean? That means that we've done something, and we've actually done what we kind of set out to do here. Well, we have this assignment here that takes topological space X and produces for us, well, that looks terrible. Let's not do that again. We have a topological space X that produces for us a category, the category of sheaves of sets on it. In fact, a one topos if you feel fancy about it. And well, what does that do? That actually factors through this sobrification process. And now this guy here is actually fully faithful. Right, because sheaves are sufficient to reconstruct the lattice of opens, and the lattice of opens is sufficient to reconstruct the sobrification. And so this is a nice situation that pretty well matches what I told you about, but you might start to object here that it's not a perfect match for the story that I was telling you. And the objection might be that, well, you know, what we're saying here is that I of X, we're turning that into, you know, X tilde less than or equal to 0. This doesn't look like a representation category. This doesn't look like a functor category.
Yeah, I was just going to ask, I think relatedly, what is the relationship between their lattices of opens, X and its sobrification?
They're the same.
Ah, okay.
They're exactly the same.
Oh, do they have the same growth motif topology? Or
Yeah. Yeah,
they do.
So this lattice of opens thing he's talking about lives in this category of frames, and so this is like you have a functor from topological spaces to the opposite category of frames, and there's an adjunction, and sort of it restricts on sober spaces on one side and on something else on the other side to an equivalence of categories. So that's what's going on here.
Ah, okay, perfect, great. So it's like tautological. That sheaves on I of X are the same as sheaves on X in particular.
Yeah, yeah. Well, as soon as you know that fact about I of X, yeah.
As a result of that fact.
Right,
Yeah.
exactly, yeah. Yeah. Yeah, the opens are precisely in one-to-one correspondence. I should have said that earlier, thank you. Other questions? So this doesn't look like a functor category, but we'll come back to that. But maybe I'll just give one example that sort of indicates that it looks a little more like a functor category than you might think, which is this circumstance where we had a poset P, finite poset P. So if P is a finite poset, then it turns out that when you look at sheaves on P, then this is actually the same thing as just functors from P into sets.
Actually, you don't need finiteness for this at this point, but you need it later when you do spaces.
Yeah, that's right.
It's true for any poset, actually.
I'm going to put the finite in parentheses, but Peter's quite right. As usual, Peter's quite right. The finiteness here isn't strictly necessary for this sentence, but in a little while, I'm going to take the word set here and replace it with space, and then I will need something like finiteness for that sentence. Yeah, so just to be cautious, I'm going to stick with the finite assumption just so we don't betray ourselves. So this is a sense in which the sheaves really do look like functors out of something. That's the point that I wanted to make.
Oh, and maybe it's useful to say that this is just because the things that are P greater than or equal to some element form a basis for the topology.
Yeah, so if I look at P greater than or equal to some little p, then this is a basis for the topology. And as soon as you know that, this consequence becomes pretty immediate. Well, at least swiftly, if not immediately.
What must be checked? Like a sort of, some sort of, like the question of what are the covers among these basis elements or something?
Can you repeat that? Sorry.
What must be checked to deduce from knowing that those are a basis? Is the question one of like what are the covers among those opens?
No. As soon as you have a basis, this sentence. If you have a topological space with a basis, this sentence is true. The sheaves on it are sheaves on that basis.
It's like in the Stacks project called the B-sheaf condition.
Oh, is it? Okay. Harry says that it's in the Stacks project.
Yeah, it's B-sheaf, and you can search for that, and it's a condition for whether something's a sheaf based on being satisfying a condition for the basis only.
Yeah. Also, in I believe section B.6 of Lurie's paper on ultra categories, there's a really nice exposition about bases for growth-induced topologies. And so, yeah, it's just applying a general fact about bases for growth-induced topologies.
Oh, I'm sorry. Does a basis mean that functors out of it are sheaves on the whole thing, or is there still a sheaf should I think basis in the sense of sheaf module or projective module? Okay, great.
Yeah, sorry. There'd normally be. I understand your point. Yeah, sorry.
Yeah,
I misunderstood what you were asking. Yes, normally there would be a sheaf condition, but in this case, there's no sheaf condition because we've already worked our way all the way down to writing down the stalks. This is one of these situations in which the stalk of a sheaf is actually the value on a particular open set, namely this open set right here.
That's the stalk at little p.
Yeah, if I take the value of my sheaf on that, then that will be the stalk at p.
Because that's the minimal open that contains.
That's the minimal open. So there's that colimit stops pretty early.
Yeah. Very cool.
Okay. So so that's the story. If you take sort of the biggest category of sheaves of sets that we can think of, namely all of them. And here I've just been talking about topological spaces, but that's okay for the moment. But then I can restrict and look at a very tiny class of sheaves. And so that's what I'm going to do next. I'm going to look at a very small class of sheaves of sets. And I'm going to try and understand the smallest class of sheaves of sets that I can, which is the class of constant sheaves. So of course, your immediate objection is that, well, the category of constant sheaves on X is also, the category of sets, right? Because there's just nothing else to say. But what are the values of a constant sheaf, right? So if I take a constant sheaf on a set, and so what does that mean that I've done here? That means that I've pulled it back using this to X. I've taken my set S and I'm looking at the constant sheaf on it, and then I'm going to take global sections on it. right? And the question is, what is that long functor? And of course, one of the things that you learn when you first learn about sheaves is that constant sheaves are not constant as pre-sheaves. And so, and that's because of the sheavification that's implicit in this functor right here. So what does that mean? That means that I've got a functor here from the category of sets to the category of sets. And it could do something interesting to a set with 2 elements, say. If I start off here with a set with just 1 element, then the result that I'd get would just have 1 element. But if I start with a set with 2 elements, then I could get anything at all. I just don't know. It'll have to depend on something. It'll have to tell me something non-trivial about X. So the question is, what is that something? Yeah, Peter.
So your gamma upper star, this is a constant sheaf functor, and then gamma lower star is its right adjoint, aka global sections, aka evaluating on X.
That's the constant sheaf functor, that's right. And this is, oops. And this is global sections.
So you just told us this composite always preserves the terminal object.
That's right. This composite always preserves the terminal object. In fact, it does even better than that. This functor not only just preserves the constant object, but it even preserves all finite limits. Is that legible when I write that small? Not terribly, huh?
Yeah, no, it's fine.
Yeah, I can read it.
Okay. So that actually preserves all finite limits. So it preserves products, it preserves fiber products, it preserves your terminal object. Not only that, but these functors are both accessible. So that makes this thing a pro set. And so that's what I'm going to define in general right now, because this is going to be something that'll be haunting us for the rest of the semester as well. So I might as well tell you that a pro object of a category, and in fact, for those of you wishing to skip ahead, this definition works fine for an infinity category. Well, actually, hang on, I'll go back to that later. A pro object of a category C is a left exact. Left exact for me just means that it preserves all finite limits. Accessible functor. From our friend C to the category of sets. If I wanted to do this, what's that?
Am I assuming C has finite limits and is accessible?
Yeah, I better do that, huh? Yeah, let's do that. Let's assume that this has finite limits and is accessible. Otherwise, this won't make a hell of a lot of sense as a definition. So you might have seen this kind of definition before where this word wasn't showing up. This word is just there to deal with the fact that the category C a priori can be a large category. It doesn't have to be a small category.
Out of curiosity, is there a word for accessible categories with finite limits?
I don't know of one. Do you know of a word for that notion, Peter?
Have a word for that, wouldn't it?
No, it would be convenient to, yeah. I always have to say this accessible category with finite limits, which is kind of annoying.
I know.
That's kind of a fumbly phrase, isn't it?
Yeah, okay.
What should they be called?
Thinking caps, guys.
Okay, so that's your first homework problem for this semester.
Well, maybe I've seen some like very cheeky thing like lexessable or something that I could never pronounce really. Or no, I think it's like L-E-X.
Oh, it's L-E. Oh, I see. I've got to have the.
Harry says pre-pro category.
In what sense are these pro categories or pro anything?
In what sense?
I mean, accessible means
it's a joke. It's a joke. I put a little smiley face frowning.
Oh, but is there mathematical content then, or you're just being silly? Which is totally.
Well, they're the things that you need in order to define pro objects.
Well, I mean.
Oh, I see what you mean. Okay, I was thinking.
I mean,
because accessible, am I right? It just means that you are like int kappa for some sufficiently large kappa.
That's right.
Of your kappa compacts. Okay.
That's right. So but maybe part of what Harry is saying is that, let me change color just to make this a little more legible maybe, that you have this functor from C to, well, I'll call it pro C, but I'll emphasize a kind of tricky point, which is that this is the category of functors from C to sets that satisfy this property. So they're left exact and they're accessible, but I have to take an op here. Otherwise the Oneida embedding won't go the right way. And then if you do that, then this is a fully faithful functor. So every object of one of these C's can be regarded as a constant pro object. Whether or not that makes you happy as a pre-pro category, I don't know, but it's
Clark,
it makes me unhappy.
What's that, David?
Is it clear that this agrees with ind C op?
It agrees with ind C op in the case where C is small.
Okay.
So all small categories are automatically accessible because there's just nothing really to say about them.
Yeah.
Sorry, all small idempotent complete categories, right. My apologies, are automatically accessible. And so if you're small and idempotent complete, then this is ind. Well, let's see, maybe I better add a new page instead of junking up this one. So if C is small and idempotent complete, then pro of C op, I'm going to try and get this right. Well, okay, maybe I could do it the other way. Pro of C is the same thing as ind of C op op. But in general, not. What's that?
Do you really need these assumptions? Because, I mean, both sides have a universal property, and I mean, you can prove that the definition you gave of pro C satisfies the universal.
That's right.
Universal property.
That's right. I could probably erase the idempotent completeness. However, I really doubt that I can replace the smallness. But the issue is just that I don't know what this side means.
Sorry, is this really a special case of the previous definition, or is it just compatible in some way?
It's a special case of the previous definition.
And how is a small, like with respect to what cardinal are we talking then? If we have like a small category, it's supposed to be accessible or like kappa accessible?
This is like a annoying calculation that I think is done in this book by Adamek and Rositsky.
No, it's something simpler. It's simpler. It's what am I supposed to say? Just say it's right.
Like I thought accessible meant generally like large but controlled by small data, and then
all small categories are accessible.
If the category is small, you can just write out its multiplication table and you're done. I mean, you know, there's.
Well, that's fine. I'm just asking about what does accessible,
I mean,
or in what sense is that accessible?
I assume that it's essentially trivially accessible.
Yeah, I think maybe the cardinal is actually 0.
Yeah.
Is that right?
I thought that you need idempotent completeness for it to be accessible.
Is that right? Is that right, Harry? Do I need?
Yeah,
I wrote that
because
down, but then I erased it.
Yeah, you do need it. It's because like you have this calculation where you show that you can get all of these idempotents from like really huge filtered colimits of some size, and like you have to do some sort of cardinality estimate, and that's what I'm
the thing
saying is I think is a little bit complicated.
That's the thing you're referring to.
You just need filtered colimits for some cardinal greater than omega to force idempotent completeness.
I mean, in the small case, shouldn't pro C be just left exact functors from C to sets all opt?
Yeah, that's
exactly.
right.
That was my concern.
Yeah.
And I think taking cap equals 0 addresses that. So thanks for clearing that up. Appreciate it.
But I mean, I think there is a point here, but I remember that there's always this funny business and I have to dance around it. So, right, there's this incompatibility between, it's not an incompatibility, it's just a sort of weird way in which the definitions overlap of different forms of pro C. But what Peter says is right. If C is small, then pro C should just mean left exact functors from C to sets. But if C is not small, then I have to say accessible. And then those two things coincide in this particular case where C is small and idempotent complete. That's the thing that I should have said.
Yeah. But then, yeah, this thing with the pro C being in blah, blah, blah. Right, if you, from the universal property of pro C given by formally adjoining co-filtered limits,
yep,
then it's clear that it's in C op.
Yeah, that's right. So maybe that's a good point. So let's write down the universal property that Peter wants me to write down. So universal property. And let's see here. So the universal property is going to be that if D has all inverse limits, so inverse for me means co-filtered. And is accessible, then, well, okay, so let's see here. So what are functors from pro C into D that preserve inverse limits? Well, they're exactly the same things as functors from C into D. Full stop. So what is that saying? That's saying that pro C is constructed from C by adjoining formal inverse limits of the objects of C. That's the thing you wanted me to write down, right, Peter? Okay, good. All right. And so that's the situation. By the way, what does that mean? That means that in particular, one of the things that I'm saying here is that, I mean, it's not obvious that this is a particular case of what I'm about to say, but in order to prove this theorem, one of the things you have to check is that everything in pro C can be written as an inverse limit, where the xi's are all actually in C. And often you'll see people put little quotes around this limit in order to remind you, to warn you that in fact this limit isn't to be taken in C, it's to be taken in the pro category. It's taken in this formal sense. So if you look in Deline's SGA 4.5, for example, he uses this quotation notation quite a lot. Okay. Whoops. What was I doing? I forgot now. Oh, right, I have a proposition. Here's a proposition. Right, so remember what the story was. Let's go back. So the story was I defined a pro set, a pro object in the category of sets, which was pi naught top. So top stands for topos. This is the sort of topos theoretic pi 0 of our topological space X. And we're going to get it just by trying to think really hard about constant sheaves. So we're going to look at a set, and we're going to take the constant sheaf on X at that set, and then we're going to look at the global sections of it, and that's going to define for us a functor from sets to sets. And that functor from sets to sets is really maps out of a pro object. That's how you want to think of this. So maybe I should emphasize that point, actually, by the way. Often, instead of, when you think of this, let me just do this in the case, actually, no. When you think of one of these left exact accessible functors, what we often do is we often refer to that as maps out of F into blank, right? And that makes it clear and the blank here is something where you can put any object of X, and that makes it clear that this thing is an extension of the category C. We're using our Yoneda embedding. Is that notation okay for everybody? Peter's nodding. Some of you, I can't tell whether you're nodding.
I'm nodding.
Yeah, that seems good.
Is that okay? So the point here is that maybe let me just actually make a little more space down here. Come on, bigger eraser. There we go. Let me erase this universal property just to sort of show you how this thing works in practice, just in case this is new territory. So if F is one of these pro objects, then I'm going to use this notation here. And then, so what did I say? I said that F could always be written as this kind of formal inverse limit of objects xi, where the xi's are all in C. So you can always write it as this formal inverse limit. Sorry, I put the inverse, the quotation marks in the wrong place. So what happens? Well, now I'm looking at, say, F of some object of X, let's call it Y. I'll also write that as maps from F, regarded now as a pro object, not just as a functor, into Y. But that's the same thing as maps from this limit, which is in quotation marks. And now the way the calculus of these things works is that when you've got a map from a limit in quotation marks, you're allowed to pull that out to just if it's a map out of a limit to just a plain object, you're allowed to pull that limit out and make it into a colimit. And so that makes this a colimit over I and I op from maps from xi into y. That's how this little game is played. Does that make everybody happy?
Yup.
Good, it makes me happy. Okay, so this is the way the calculus of these pro objects works, and that's part of the game that we'll play. So let's play that game. So I have a proposition. My proposition is that this particular pro object that we wrote down, pi naught top of x, if I map that into some random set S, so this is just a set, then that's the same thing as fun lower star. What does that mean? So this means morphisms of topoi. And these are one topoi.
What's a map of one topoi?
What's that?
What's a map of one topoi?
I shall tell you. A map of one topoi is a, by the way, these are also called geometric morphisms is the other phrase, and I'll use that phrase too. Geometric morphisms. So what is it? Well, it's going to be a functor from this thing. By the way, I should tell you what S tilde is. I'll tell you that in a sec. But for now, just know that it's a topos. So it's a functor, which is usually denoted by a lower star, F lower star, that admits a left adjoint, which is usually called F upper star. And the requirement is that that left adjoint be left exact. The requirement is that that left adjoint be left exact. So a morphism of topoi is a right adjoint to a left adjoint, and that left adjoint preserves finite limits. You don't normally expect left adjoints to preserve any kind of limits, but in this case, you're going to demand that they preserve finite limits. So that's all it is. It's a completely categorical notion, but it accurately reflects the kind of structure that you have when you're thinking about topological spaces. So for example, when I've got a morphism, or sorry, a continuous map, as they're also known, from X to Y, then on the category of sheaves, I have an induced geometric morphism from sheaves on X to sheaves on Y. So the lower star goes in the same direction as the continuous map. and the upper star goes in the wrong direction. Everybody happy? Okay, so I have to tell you what this S tilde is here, so I better do that. So this S tilde, what is that? This is just, these are like sheaves on the set S, right? S with the discrete topology. If I look at sheaves on it, then I can understand those pretty well. Those are really just the same thing as functors from S into sets. This is just a lazy notation, that's all. Okay, so now I want to try and prove this proposition for you. And it's going to require an idea that is going to come back to us in several different forms. So here we go. So I'm interested in trying to understand this mapping space right here. And I'm trying to understand maps from pi naught top of X to S, right? So this is a map from a pro set into a set, and I'm trying to understand it. And well, by definition, that's the same thing as the value on S of gamma upper star, gamma lower star. That's just the definition that we gave pi naught top, right? We just told it to be that. Okay, so let's think here. So I'm looking at the global sections of the constant sheaf at S. That's the same thing as the mapping space in the topos in the category of sheaves on X from the terminal object, which I'm calling 1 here, into the constant sheaf at S. Right? These things are exactly the same. So these are just two ways of writing global sections. These are both just saying global sections of gamma upper star of S. And it's just two ways of saying the same thing. Okay, but now I have the job of trying to understand maps from the terminal object to gamma upper star of S. And for that, I want to tell you a cool lemma. This is a lemma that's about a general morphism of topoi and a general object, right? So the situation here is that you should imagine, let's see, what's a good imagination color? Blue, teal seems kind of imagine-y. So here you should think of X as X tilde less than or equal to 0, and Y as the category of sets, okay? And U here is going to be that set little s that we were talking about. And what's going to happen is that if you've got such a geometric morphism, it goes like this. If you've got a geometric morphism of topoi, and you have an object at the target topos, then maps in X from 1 to the pullback of that object actually can be written down in a particular way. They're the same things as the geometric morphisms from X to the slice topos. This is the category of objects over U.
So I have a stupid question.
Yes.
The thing on the left is a set. The thing on the right is
That's not a stupid question.
Category.
Yeah, that's a correct question. But I'm noticing now, before I answer that correct question, let me emphasize that I should have added something to this notation, namely, I want to preserve the natural geometric morphism down to Y. Right, so these are topos theoretic morphisms, geometric morphisms from X to Y over U with the property that this diagram commutes up to a specified natural transformation. So this is F lower star. This would be the new map that I wrote down. This thing here is the new map that I would write down. And then this is just what you might call P lower star. So this is another geometric morphism that is canonically there. It corresponds to, maybe I'll just say, it's the right adjoint of the functor P upper star, which is actually just taking the product with U. That's all that is. I don't know why I wrote it so poorly, I'm sorry. Blank producted with U, there we go. And so that functor there has a right adjoint, which is this one. It's kind of like sections relative to U. That's what it is. And Harry's absolutely right. A priori, this guy would be some category. You'd have a category of these functors, right? Because you'd have functors and natural transformations between them. But part of what I'm telling you here is that that category is equivalent to a set. That's not obvious. It turns out to be true. Should I give some indication of how this is proved? This is actually something that we're going to see somewhat, but we're going to see this again later. So maybe I should I give a proof? Are y'all bored? Should I try to give a proof?
Give a
Just
proof.
do the general case.
Give
Later.
proof.
Okay, good.
Maybe
The masses are
before you
chanting.
maybe before you start the proof, it's also worth saying, so this P upper star that's product with U, right? That's left adjoint, or that's right adjoint to the forgetful functor. So you have a chain of 3 adjoints relating the topoid.
Yeah, let me write that down more carefully. Thanks, Peter. Yeah, so when you look at Y over U here, and you look at Y, well, what can you do? Well, one thing you can do is just forget. And now that's not actually part of a geometric morphism of topoi in general. That's just a functor, which goes by the name P lower shriek. Now, right adjoint to that is this functor P upper star, which is taking the product with U, right? It's just producting up. And now right adjoint to that is your actual geometric morphism, which is P lower star. That might seem a little perverse, but that's the way the structure works. So the actual geometric morphism is not the forgetful functor, it's the other one. It's the extreme adjoint on the other side. If I'm going to be given a proof, I better. Okay, so let's try and do the proof. Or let me at least tell you what the correspondence between the two sides is as best I can. So let me try to give this. This isn't quite a proof. This is going to be a sketch. I'm going to construct for you what you need to check, and then you can check. Okay, so let's say that I start with something on the left-hand side. So let's say that I start with something, a natural transformation, call it eta. Sorry, I didn't mean to say natural, just a map, eta, from 1 to f upper star of U. Let's suppose I start there. All right, now what I want to get out of this is I want to get a geometric morphism from x to y over U. So that will have a left adjoint. So what I want is I'm going to try and give you a prescription to write down the left adjoint. So I want a way to take an object over U and produce an object over X. I want to do so in a way that, well, if I started with an object of Y, I producted up with U, and then I went over by this new morphism. So maybe I'll call it capital P or something, P upper star, that I would get the morphism that I started with, F upper star. The left adjoint to the geometric morphism that I started with. Okay, so that's what I want.
Capital P upper star here is a function of eta?
Yeah, capital P is going to be something that I build using eta.
Okay, thanks.
Yeah.
Great.
Thanks. Maybe I should give it a name that reflects that fact.
H upper.
What's that? Oh yeah, H. I'll do capital A. Good idea.
Yeah, it doesn't capital
Capital
eta.
eta.
H.
No, he just wrote a capital eta is what happened.
It's a capital eta. It's perfect.
Yeah.
Okay, great. So I'm going to do a capital eta, and I'm going to construct capital eta for you. All right, so what do I want to do? Well, I want to take an object V over U, and I'm going to try and produce an object of X. Okay, so what I already know how to do, because I have F upper star, is I already know how to take F upper star of V and F upper star of U. I know how to do that. That I have available to me. And well, I've got my eta, which is my little eta, which is a map from 1 into f upper star of u. And so I'll define capital eta of v as this pullback. And that's the prescription. Right, so that's how you take a little eta and you turn it into a big eta. So that's the map going in this direction. Is everybody happy with that? Okay, so assuming that you are, then how do I go back? Let's figure out how I go back. That will require remembering how I go back. So there, what am I doing? I'm starting with a capital eta. So let me see.
Sorry, could you actually go back so that
Yeah,
we
of
can
course.
see them both at once?
Oh,
or
yeah,
maybe
sorry.
just copy and paste or something.
Let me copy and paste, yeah, sorry. Thank you. I'll copy and
So
paste.
one point here is that this eta commutes with colimits and finite limits, one by construction and the other because of toposness.
Yeah, that's right. The
colimits.
Yeah, that's right.
Like
so
colimits are universal thing.
Colimits are universal. That's exactly right. So f upper star preserves finite limits and all colimits, and so this h upper star preserves finite limits, and then it also preserves all colimits because colimits are universal. That's exactly right. That's exactly right. So let me see if I can figure out how the construction goes backwards. So suppose that I have a capital eta. I'm going to try and get a little eta out of it. So let's see if I can do that without too many mistakes. And this is P upper star again. This is that product with H thing. All right. And so what do I want? I want to get, okay, I think I see what to do. Okay, so what do I want? I want to get myself a little eta. I want to map a global section, if you like, of f upper star of u, right? That's what I want. I want a global section of f upper star of u. And well, what happens here? So suppose that I have this situation. So what is f upper star of u? Let's just write that down for a second. So f upper star of u, well, it's the same thing as h upper star of p upper star of u. Right? It's the same thing as h upper star of p upper star of u. And now, well, let's think about what p upper star of u really means. P upper star of u means that I took u and I producted it with itself and remembered the projection, the second projection onto u. So I have u cross u mapping to u via the second projection. Right, so that's what this is. It's u cross u. Sorry, that's what p upper star is. It's u cross u with the second projection. Right, so p upper star of u is the same thing as u cross u with the second projection down to u. Well, and I have a map from u to u cross u, namely the diagonal, that lies over that. Now, u is the terminal object in y over u, right? So that means that I'm entitled to look at h upper star of u, but u is the terminal object, so h upper star of u is really just the terminal object of x. And so there's my map, little eta. So now I've given you the recipe for how to do this in both directions, at least sort of on objects. And so I guess I'll leave it to you to see that this is in fact an equivalence of categories. Is everybody happy with that? That's the prescription.
So maybe this is dumb, but here we have this actual identification between f upper star u and h upper star, p upper star u. I'm like, yeah. At least in the definition originally, you said that there's a specified natural transformation.
That's right.
So do we need to be careful, or natural isomorphism rather? So do we need to be careful, or is it just one of these things where it just
we don't need to be careful. You can treat that. Yeah, I said that there was a specified natural transformation, so you can treat that like an identity everywhere we've used it here. There's no secret nonsense happening there. It's really, you can treat it like the identity. It's okay.
All right.
If you're a univalence person, you would treat it like the identity.
I mean, effectively, in the construction, you're just kind of carrying it along for the ride, and you implement the isomorphism whenever you need to.
That's right. Yeah. So I mean, here, for example, I've got a natural isomorphism that I'm bringing along with me, and I'm using that to transport the thing. But yeah, it's already specified, and there's no coherence problems because there's so few diagrams to cohere that there's nothing going on. I'm starting to get kind of bright here, so let me just pull this down. Here we go. Here we go. All right. So what did we do? So the whole point of this exercise was to show the equivalence between these things here. So I was looking at maps inside the topos X from 1 to F upper star of U, the global sections of F upper star of U. And on the other side, I was looking over here at functors from X into Y over U that respect this geometric morphism here. Okay. And why was that relevant? Well, that was because I was looking at global sections of F upper star, but that's precisely the kind of thing that I reduced this problem to over here. You see in this topos here, in the topos of sheaves on my topological space X, I was looking at global sections of the constant sheaf at S, right? That's what I was interested in, was global sections of the constant sheaf. But now I have an identity for the global sections of the constant sheaf using this interesting lemma. So, by the way, just for those of you who are curious about such things, the map here, this geometric morphism here, geometric morphisms of this shape are called étale. So if you want to read more about it, if you look up étale geometric morphisms, that will help you find lots of information. So, okay, so how do I finish off the theorem now? Sorry, I was going to try and finish the theorem. Where am I going? Okay, here we go. I'm trying to finish off the theorem. Let's do that. So what do I have here? Well, I have an equivalence between maps from 1 to gamma upper star of S and, well, geometric morphisms over the category of sets from sheaves on X to the category of sets over S, but that's the same thing as S tilde. That's the same thing as this category of functors from S to set. And so now, well, I've proved my theorem because everything has a unique geometric morphism to the category of sets. And so the proof is over. So now I get to draw this box. Okay, so now why did I want to prove this? Why did I talk about this in the first place? Well, I want to talk about this because this reminds you of something that you know about topological spaces. If you think in the world of topological spaces, by the way, let me just pause and notice that this didn't really have anything to do with X being a topological space. The same thing would have worked perfectly if X were a general topos. The topological space is receded into the background for the purposes of this proposition. Right. All we care about is its topos of sheaves. We've just forgotten about X for a little while. But what's interesting here is that this is really the kind of thing that we'd like to be true for pi naught of a topological space. It isn't quite true for a general topological space, but it's true for some of them. It's not true that, that if you look at the functor that carries a discrete set to, the functor that carries a set to the discrete topological space with that underlying set, that functor doesn't quite have a left adjoint, but it does if you restrict the class of topological spaces a little bit. And so then that allows you to arrive at the following theorem, which is that if X is a topological space that is both sober and numerically generated, then this topos theoretic pi naught is actually pi naught of your friend, the topological space, as you know it and love it.
What's a numerically generated topological space?
Peter wants to know what a numerically generated Peter and I met over the definition of a numerically generated topological space. So, but he's performing his role as a Greek chorus. So.
Oh wait, I actually have a question.
Yeah.
This pi zero on the right is not path components. It's like literal connected components.
It doesn't matter for a numerically generated topological space.
Okay.
That's the beauty of numerically generated topological spaces. Yeah, so let's see. I'm not giving the proof because the proof The proof is that these are both left adjoints to the forgetful functor, and when you're sober, there's no difference between being a topos morphism and a continuous map. But I was going to remind you what numerically generated means. So definition, our topological space friend X here is numerically generated. I'm just going to write numgen out of laziness. If and only if, I'm going to do a stylistically bad thing here, and I'm going to say X is numerically generated if and only if all numerically open sets are open. And now you'll have to ask, what is a numerically open set? So I'll say that U inside X is numerically open if and only if for any continuous map phi from the interval into X, phi inverse of U is open.
That's the closed interval with its usual topology?
Yeah, that's the closed interval with its usual topology. I deliberately chose that out of laziness. I could have been more methodical if I chose to be. I could have taken here a lot of different things. I could have taken anything inside the topological simplices. I could have taken Rn or open subsets thereof. And they would all give you the same class of topological spaces.
So any one of those would have sufficed?
Yeah, I could have.
Okay.
That's right.
You have to use a space filling curve argument to show that one of these things is equivalent to this one-dimensional thing. But
yeah, it's a fun argument if you've never seen that before.
That is crazy.
It's one of my favorite ways to torture undergraduates, one of whom was Peter.
yeah.
7 years ago or something.
By the way, which way does the map go from pi 0 to path components? Harry alluded to two different definitions of pi 0. Path components
between
and
path components and components?
Yeah, and what's the relationship is, I guess what I'm asking.
Right, so for a general topological space, if you look at the, wait, I know how to do this. If 2 points are connected by a path, then they're in the same path component.
Ah, yes, right.
Right.
So pi 0, as we've defined it, maps to the other thing.
There can be more path components than connected components.
Yeah, isn't
That's
it
right.
like a quotient, basically?
Yeah.
Yeah, so right. So let me just say this correctly here. So I'm going to write path here, and then this is like just the usual connected components here. And there's a map like that, which is actually a surjection.
Surjection. Okay.
And but in the case where you're numerically open, these two things are just equal. There's no difference. Path components and connected components are the same.
But
So
is that if and only if for numerically generated?
What's that? Say it again.
Why didn't you just state that condition, that the path components and the connected components agree?
Well, is that if only?
I could have done. You mean in the theorem?
Yeah.
In place of, yeah, I should have probably, but I just, felt like saying that there was a codifiable way to say when that happened.
Cool.
That was a reasonably good category.
Oh yeah, isn't the category of numerically generated spaces also presentable?
Yeah, it's a presentable category. So it's presentable. It's Cartesian closed. It's a good category for topology, or for homotopy theory.
And posets in the poset topology, are those numerically generated?
They are. I learned that from you. Other questions? So what's the point of all this? What was I getting at here? The thing that I was getting at was that if you really thought carefully about constant sheaves, then for at least a pretty big class of topological spaces, i.e. the ones that are both sober and numerically generated, then you'd extract an invariant, which was a priori a pro set, which is something relatively exotic. But in fact, it's actually just a set, and it's a familiar set. It's the set of connected components. And for this class of topological spaces, it doesn't really matter whether I say connected components or path components. Okay. So, however, the story that I was trying to tell was that when you extracted one of these kind of homotopy type things, something like this guy here, that functors out of it was going to be the thing that recovered your category of sheaves. The category of sheaves that we started with contemplating was the category of constant sheaves. Excuse me, but if I look at functors from the set of connected components of a space to the category of sets, that's certainly not going to be just the category of constant sheaves, right? You're going to pick up some other locally constant sheaves that are not listed here. On the other hand, it includes some of the locally constant sheaves, but it doesn't include all of them. It only gets up some of the locally constant sheaves. So the question is, if you want to try and understand the locally constant sheaves, what more information do you have to input? So let's look at A of X being the category of locally constant sheaves of sets on X. By the way, I mean, I'm talking about all this stuff because I mean, some of this story is probably familiar to a lot of you in perhaps a slightly different language, or maybe you've had access to it in a different way. So, I mean, it's okay if some of what I'm saying is either boring or unfamiliar. Both of these possibilities can coexist normally. There's nothing bad happens if that's the case. I just don't want anyone to feel left out, either from boredom or confusion. Okay, so we're going to talk about locally constant sheaves of sets. And so what are those? Those are sheaves with the property that you have an open cover of your space, and on each bit of that open cover, you can express that sheaf as a constant sheaf. So that's what locally constant means. And right away, we start to have our concerns that this is an interesting theory, because I write down one of the simplest topological spaces, namely the interval, and I discover it doesn't have any interesting locally constant sheaves. They're all constant. So let me explain why that is, because it'll be indicative. So what can happen? So I'll start off with my interval here. And well, there's a local constancy means that there's an open cover of this interval with the property that on each piece of that open cover, I'm actually staring at a constant sheaf for some set. I don't know what it's constant at, it's constant at something. So on each piece of this, I'm looking at a constant sheaf. And well, if I have such a cover, then I could refine that cover to one that consists only of intervals, right? And if I can refine it to one that consists only of intervals, then I've got a trivializing open cover consisting only of intervals, but it's an open cover of the interval, so I might as well take it to be finite, right? So in other words, I have a finite open cover of this thing exclusively using intervals. And over each piece of this open cover, I've actually got a constant sheaf. Okay, so now let's see what happens. So I don't know how many of these I have, but I have a few of them, but there's only finitely many because I can just reduce to that case if I need to. So now let's look at two of them. So I'm constant along this open interval, and I'm constant along this open interval. Well, and if I'm constant along each of those things, the overlap here is just another interval. And there it's certainly constant because it was constant on each piece, so it certainly is constant on the overlap. And if it's constant on the overlap, well, it's connected, right? And as we saw last time with connected things, the constant sheaves are actually constant as pre-sheaves. the sentence I just said wasn't right, but the global sections of the constant sheaf are just the underlying set. That's what I meant to say. It's not true they're constant as pre-sheaves. That wasn't the right thing to say. What I should have said was that their global sections are just the set at which you're constant. That's what I should have said. Okay, so what does that mean? That means that, well, it's constant along here, and it's constant along here, and this intersection here is connected. So that means that it's constant along the whole thing. But what did I do? I took my trivializing open cover, which let's say had 9 elements in it, and I just found that I could union 2 of them and still have a trivializing open cover. So now I have 8 elements in my trivializing open cover. And well, now I'll just induct my way down until I have just one thing in my trivializing open cover, and that'll be the interval itself. Okay. So let's take a moment to realize that that argument doesn't work as soon as I get to be the circle. Right? As soon as I get to be the circle, then I'm going to have a bunch of non-constant, locally constant sheaves. And to show you why, well, one thing you can do is you can think of, for example, here's an example of a non-constant, locally constant sheaf. You can look at the squared map from S1 to itself, and you could look at the sheaf of sections of that. And the sheaf of sections of that is not going to be constant, but it's certainly going to be locally constant. And the reason it's not constant is that it hasn't got any global sections. And the reason it doesn't have any global sections is because that you can't take the positive square root of any complex number. That's the same story. Okay, so but what went wrong in the previous argument? That's the point that I really want to come around to. So for example, for this particular sheaf, there is an open cover. There is an open cover of the circle consisting of intervals relative to which, so there's one interval that goes this way on the top, and there's another interval that goes the other way on the bottom. And on each piece, you've got a nice trivial sheaf, right? The sheaf is actually constant. However, the overlap between these two open sets is not connected anymore, right? It's a disconnected thing. That fact alone is what's at stake here. That fact alone. So what am I saying? What am I saying? I'm saying that if you've got a open cover of your space with the property that it's a trivializing open cover, and any intersection of 2 of those things pairwise is connected. I don't require anything more than connected, just connected. Then in fact, you're globally constant. Your sheaf is globally constant. But that isn't true here, and it's precisely because these 2 things form a non-connected space. And so now I'm in trouble. And that trouble exactly guarantees for me that I have this non-constancy. So if you're fully embedded in homotopy theory, then what you're thinking when I've drawn this picture is that what I've really done here is I've exhibited S1 as a certain pushout, homotopy pushout, as a pushout of something contractible with something contractible, and I've unioned it under something contractible, union something contractible. And that somehow this homotopical representation of S1 is really what's provided for me this non-constant, locally constant sheaf. Right? And that's exactly right. That's exactly the truth, is that this homotopy decomposition is precisely what's providing me with these locally constant sheaves. So let's see what's going on here. Excuse me. Okay, so suppose that I've got a random topological space X. And suppose that I have a locally constant sheaf on this thing. My advisor always drew sheaves like this as arrows down to the space. And I always wondered what he meant when he drew that, because a sheaf for me was just a functor. But now I found myself doing exactly the same thing. So I don't know. Okay, so this is a locally constant sheaf. And now suppose that I have 2 points, x and y, and I have a path going between them. Okay, so that path is this interval mapping in, and so I'm entitled to form gamma upper star of L. That's now a locally constant sheaf on the interval, but that has to be constant, right? Locally constant sheaves on the interval are easy to come by, they're just the constant sheaves. So what does that give you? Well, if I go further and I pull back to the stalk, let's see. If I go further, I can pull back either to this point or to that point, the 2 endpoints, that is. And so I can look at the stalk at x or the stalk at y. And well, these are all isomorphic canonically. Right? Here, what I mean by this is that this thing is a constant sheaf at a particular set, and that set is canonically isomorphic to this and to this. Right? So that produces, in particular, an isomorphism from here to here, if you just compose these things. So what does that do? That gives me a way to take any path inside X and produce for me a isomorphism from the stalk at X to the stalk at Y.
So this L sub X or Y is what you previously denoted by X upper star.
Yeah, thank you.
L.
Yeah, this is just the stalk. That's right. Thanks.
This makes me wonder, under what circumstances, so the L mapping down to X, I imagine, is some espace étalé construction. Under what hypotheses on X is that an equivalence?
Between the espace étalé and the category of sheaves?
Locally constant sheaves.
Well, so locally constant sheaves correspond to covering spaces. And the espace étalé, so like what is it called? Local homeomorphisms correspond to sheaves, I think, really
with
often.
no conditions.
Is it no condition at all here?
No
I don't think there are any conditions.
Harry and Peter say there are no conditions, and I'm inclined to believe them. So.
Okay, cool.
Yeah, I mean, in any case, I think it's extremely general, and I think they're probably right. I think there's probably no condition at all.
Yeah, I think there's a nice write-up of this in the Sheaves in Geometry and Logic book of Moerdijk and McLean, that they give a nice explanation of this espace étalé and local homeomorphism, etc.
Right. Cool.
Yeah, I certainly believe it for nice topology, say manifolds or something. I was just curious about the full generality. As long as we're getting nerdy about, separation axioms and so on.
Hartshorne uses it for his proof of some construction of the structure sheaf. So it's really? Like true over, Hartshorne does. That's why I hate that book, because it does everything stupidly. But anyway,
So no, but I think that's right. I think it's always true. I mean, I just drew this just to have a schematic. I don't know. Even the pullback, I think, is the pullback. So I think it's really true in general. But I was really just drawing this as a schematic for a second, because the main point that I wanted to say was that when you have this L here, what does it give you the ability to do? It gives you the ability to take points and produce stalks. And when you have paths between those points, then you have an isomorphism between the corresponding stalks. And furthermore, you can check that if you take 2 paths that happen to be homotopic, then those 2 paths actually give you the same isomorphism between the 2 stalks. And of course, you can compose these things, and that works well. So what am I going to tell you? You can all see where this is going. Then I'm going to tell you that this gives you a map from the fundamental groupoid of X to the category of sets. And so in particular, this is something that can actually tell the difference between 2 different local systems. So for example, if I have 2 local systems on the circle, then I can have 2 different representations of the integers that come about from that, right? I have two different sets with automorphisms that can come about from that. And so this thing seems to be able to detect, so this is capable of detecting, can detect differences between L's. I'll just say it like that. Okay, so this representation here that is attached to this local sheaf, this kind of representation of the fundamental groupoid is called the Menagerie representation. And what is this word menagerie all about? So the mono part means one, and the dromos part, that's like the hippodrome, and dromos means like avenue or way. And so what you're supposed to imagine here is that you have a little route that starts and ends at the same place, and you run around it once and you see what happened, right? So you take your stalk and you run around it once and you see what happened. And that would be an element of the fundamental group, and you're looking at what that element of the fundamental group does to the stalk at that point. Okay. And so this is the concept of menagerie. This is the menagerie representation corresponding to a local system. By the way, I'm being slightly lazy. I'm saying the word local system to mean locally constant sheaf. Technically, that's not perhaps the best way to use that word. Probably local system should mean a locally constant sheaf that's trivialized over a finite open cover. But I'm going to be a little murky about it because the distinction isn't very important for us right now. It will show up a little later.
What is that distinction? What does that distinction even relate to? I've never heard of that before.
What does it relate to?
I've never heard that definition of a local system. I always figured it was just what you wrote, equivalent to a representation of the fundamental groupoid.
I mean, I think it's more of an algebraic geometry thing, because in algebraic geometry, for locally constant constructible sheaves, you always have this additional thing about, well, the stalks are finite and you can always trivialize over a finite cover.
Yeah, I mean, I think if you're, I don't want to speak out of turn here. I think if you're thinking about manifolds and things, you're never going to see this distinction. Am I right about that?
Like every other term so far in this talk, pretty much, the term comes from like complex analysis, right?
Right. Yes.
And so whatever it means there is the original meaning.
That's certainly true.
As in like holomorphic.
Yeah. So that's definitely the case, is that these things were originally holomorphic, local systems. Okay. So I wanted to, so remember, what is our goal now? So our goal was to try and figure out what was going on. We'd had pi naught. Pi naught looked pretty sensible. So, okay, so I'm realizing what the time is. So, what would people have me do? Would people have me get to a punchline and then stop? Or would you have me just stop on the dime? Or what would you have me do?
How long until the punchline?
Peter wants to hear a punchline.
Sounds like a good
I
idea.
asked how long until the punchline. People might want to know that.
Right, people might be, right, that's fair enough. Okay, so, all right, let me say what the situation is then. So what happened to us? We were looking at pi naught, and the way we got to pi naught was to think about constructible sheaves of sets. Okay, and then when we looked at pi naught, we realized that what we were getting was a little piece of the theory of locally constant sheaves of sets, right? Not just constant sheaves of sets, but locally constant sheaves of sets. So we wanted to see a little more of that theory. And so what the idea here is that we're looking at this Menagerie representation, and that Menagerie representation is related to the fundamental group, which has information about pi 1 in it. So it has slightly more homotopical information about our X than we used to have. So then the question becomes, well, can I do a similar story if I talk about sheaves of groupoids instead of just sheaves of sets? So let's try that. So I'll set up exactly the same system. And exactly the same system is, well, I'll start off with the category of groupoids. I'll look at now the sheaves of groupoids on X. For those of you who have never thought about this before, I'm taking sheaves in the homotopical sense, not in some very rigid sense, but in the fully homotopical sense. So here I've got, the sheaf condition is a homotopy limit condition. It's an easy homotopy limit because these are just groupoids. I don't need the whole simplicial diagram. I could just take the first 3 stages, but still that shows up. And then I can go back down, and this will give me a functor from groupoids to groupoids, which is a left exact accessible functor, and I will consider that to be a progroupoid. That progroupoid is what I'm going to call pi1 top of X. And this pi1 top of X is sufficient to reconstruct local systems of sets. That is to say, local systems of sets on X are the same things as representations of this groupoid, right? This is a progroupoid, so this is quite a weird thing, but nevertheless, so in other words, you think of this thing here as an inverse limit of ordinary groupoids, and then this functors out of it is a co-limit of functors from those finite stages to sets. So now I can reconstruct local systems of sets. But the way that I constructed this pi1 top was by contemplating constant, right? This is the constant sheaf functor, constant sheaves of groupoids. Okay, so but once again, I'm going to wonder, well, what happens if I look at functors from pi1 top into groupoids, right? And then I'll see that I'm picking up some locally constant sheaves of groupoids, but not all locally constant sheaves of groupoids. In order to see all locally constant sheaves of groupoids, I need to go up to level 2. And so on and so forth. By the way, if we wanted to scare off our undergraduates, one of the ways we could do this is we could teach them the fundamental theorem of covering space theory as follows. If X is sober, numerically generated, and locally contractible, I could get away with less, but I don't feel like it. Then this topos theoretic pi1, this topos theoretic fundamental groupoid, is the fundamental groupoid that you know and love of the topological space. Okay, so but now we have this problem where we're trying to go up and up and up, and you can just see that, infinity plus 1 is infinity. So we might as well go on and pass to infinity, right? So here we could try and construct, if we felt like it, we could try and construct a pi2 top of X using this kind of construction. But let's just get this over with and pass to infinity. And so now here's the thing that I want us to have a look at now. So S here is going to be the infinity category of spaces. Or if you like, of infinity groupoids, or if you like, of anima, as Peter Schultz and Dustin Clausen call them. But no matter what, you can talk about this infinity category of spaces. And here we're going to look at sheaves of spaces. So that's what our friend X tilde with no subscripts is going to be. We're going to look at all sheaves of spaces. And then we're going to look at spaces again on the other side. We're going to take the constant sheaf. We're going to look at global sections. And that's going to give us this object here. Oh no, I erased it. That's not good. It's going to give us this object here, which is a pro-infinity groupoid or pro-anima. And this is sometimes called the shape of X. And well, what property does this thing have, this shape of things? Now we have this beautiful fact that because infinity plus 1 is infinity, if I look at functors out of this thing, if I look at functors out of this thing into spaces, say, then those are the same things as locally constant sheaves of spaces on X. Right. So now I really have the kind of good matchup. This is one of the big advantages of passing to infinity. You don't have this sort of awkward problem where you are constantly trying to ratchet up the homotopical level in order to catch up with the homotopical level of your coefficients. Here, the two things are living on the same level. You have the functors out of this homotopy type into spaces, and those are exactly the locally constant sheaves of spaces on X. And so now what am I telling you? I'm telling you the information that's contained in the locally constant sheaves of spaces on X is exactly the same as this homotopy type, as this pro-groupoid. And so now we have this even more fundamental theorem of covering space theory, the one that we would never ever teach our undergraduates, but still. If we had a X is above, X is a sober topological space that is, locally contractible and numerically generated, then this pro-groupoid, this pro-infinity groupoid or pro-anima, is really just the underlying homotopy type of X itself. So if you like, you can think of this in a very concrete way as the singular simplicial set attached to the topological space X. And as long as X is nice, like a CW complex or such things, then these two things are precisely the same. There's no difference between them. So in other words, this pro-groupoid, which is a priori quite an exotic object, is actually something completely understandable. And again, this is just the analog of what we already did sort of down at level 0, just ratcheted up to the infinity level. But if we try to do it at some finite stage, then we have this kind of awkward mismatch. So we just ended up passing to infinity to fix that. And here we are. So, so that's the point that I wanted to make actually for right now. So maybe this is actually a good place to stop since we're already close. So maybe the point that I want to make here is that the category of sheaves, by focusing on the category of, in this case, locally constant sheaves, we actually reconstructed the homotopy type of our CW complex, let's say. So a good topological space of some description. And well, there's this sort of, we also started off this discussion with a really, really high level thing, which is we're going to just take all sheaves of sets, and that allowed us to reconstruct our topological space always, as long as our space was something reasonable, a sober topological space. So this is where we're starting. And now where we're going to go next is we're going to start introducing more exotic kinds of homotopy types attached to our spaces, which use more elaborate kinds of sheaves. So we're going to use bigger categories of sheaves than just the locally constant guys, and that's going to get us more refined information about our topological spaces. And then we're going to be able to just do homotopy theory with exclusively those things. And that's what we're going to do, like, next.
I don't know if the clapping comes through well on my microphone. But
It's such an awkward thing.
Yeah, we're doing what we can.
That's not so bad.
Can I ask a question going back a bit? There was that proof that global sections of F upper star U was equivalent to geometric morphisms. Yeah. And there's something curious in that construction that I was trying to make sense of.
Let's see where it went. Okay, so here it is.
You've told us so much stuff. This is great. Thank you. Verbally as well as clapping wise. So there was the something that featured in the equivalence going back and forth was the diagonal map on U.
Yeah. And
I was trying to understand it in some sort of vague terms, like, so Y over U, say Y is like the big topos of somebody, and U is some object over it. And so then things over U is just like, you know, spaces over that U in some sense.
Mm-hmm.
And then I was trying to figure out what, so U cross U with the second projection is like the trivial U bundle over itself.
Yeah.
And
That's
then
exactly
this
right.
diagonal map is something, it's like remembering that over each point, there's a distinguished point called
That's right.
that point or
Yeah.
something.
Yeah, that's exactly right.
So I was wondering if that can help me intuitively with this correspondence, and or is it related to perhaps like monadicity of Y over U mapping to U, that adjunction, or just something. I just wanted to own this proof more, I guess, and that was one possible point of traction. So if anybody has anything to say, that'd be great.
Well, so maybe, and I'll bet Peter has the same thing to say, but he can actually remember how it goes. So this is actually kind of how you motivate. So there's an intrinsic characterization of an Natal map.
Yeah.
So one of these guys, of an Natal morphism of topoi. And that intrinsic characterization precisely involves a map like this.
Yeah.
This map here is actually a piece of that intrinsic characterization. So there's a very strong sense in which that map is really running the show. It's saying that
Cool.
it's saying that the topos Y over U, what's the phrase, classifies sections over U.
Cool. Yeah, that's exactly the kind of thing I'd like to understand. If you could say more.
Peter, can you say more? I'm not sure I can extemporaneously.
Yeah. Could you repeat what happened? I think there was a problem with my internet, and
sorry.
And so yeah, you froze for a second, but I'm pretty sure it's my issue.
I'm sorry. So what Aaron was saying was that if you think of this diagonal map here, can you see that? Can you see when I draw that?
Yeah.
Okay, so when you think of this diagonal map here as something that's happening over U, then you're thinking of the trivial U bundle over U, which is a weird thing to say. And then you've got this kind of funny section of it that somehow knows that every fiber has a special point in it. Right? I'm speaking intuitively, but you follow this, right? And so this is U cross U, and this is U. And then you've got this special section, which is the diagonal. And I was saying that the intrinsic characterization of an Natal morphism uses such a map, and it uses such a map, and I was trying to follow up on that, but I couldn't remember the full description of the intrinsic characterization.
Are you thinking of the base change formula?
Yeah.
Yeah. So well, let's see. I can share my screen to, I guess I could just say what the base change formula is.
I mean, if you can share your screen to write something down, that'd also be swell.
Or I can just share it to the theorem. I could also write something. You're gonna have to not share anymore.
So let me stop sharing for a second, just so I can. How do I stop doing that? Oh no, I see. Sorry, I have to do it on the thing that I'm using here. I know how these technology things work. Okay, I've stopped sharing.
So can everyone see?
Yep, I can.
Yeah. So this is a characterization of Natal geometric morphisms that's intrinsic. So it says, well, first of all, you better have this extra adjoint, this F lower shriek, which in our case was the forgetful functor. That's the first thing you need. The forgetful functor is conservative, so you're going to want that too. And then the one sort of non-obvious thing is that there's this additional base change formula. So there's always a diagram like this, and you require it to be a pullback square.
And what that, maybe I can say what that says. I'm just remembering how this works now. So if you've got something that already lives over U, let's say that X already lives over U. See if I can say this right. So X already lives over U, and you want to know what it means to base change that thing to somewhere else. The statement is that that's the same thing as base changing it over U cross U to somewhere, over U cross U to somewhere else. Ah, shoot, I'd have to write this down.
Sorry, curly X and curly Y, which is which? So the F up, it seems like F upper star is the left adjoint to the geometric morphism. So it actually goes in the other direction of what we
shit. Yeah, I'm sorry. My
our
notation exactly conflicts with this. I'm sorry.
It's okay. But so X is the Y over U, and Y is just Y?
No. So, in this...
Oh, it's the other. No, it's the other.
Yeah, annoying, right?
Yeah, this one will be like X over
the slice.
That's X over U. Yeah.
And what that object U is, it's F lower shriek of the terminal object.
Yes, it must be.
Yeah, so that's what it identifies this as.
And so you're saying, well, suppose that you have a map from Z. So Z here is just an object of your original topos, but it happens to have a map to to some Y. But that Y, let me just get this right, that Y is itself over some U. Right? And the U is the thing over which we're slicing right now.
Yeah.
Am I saying this right, Peter?
Well, maybe I should stop sharing and you can write something down, because
let me see if I can do it.
Yeah, I can also, let me in the chat, I can share. Wait, where is? Oh, I'll stop sharing this. But in the chat, I'll just share what this base change, this intrinsic characterization is. That will link to the page of higher topos theory where this is explained.
Let me see if I can. Oh, hang on. It's decided to. Okay, there we go. Let me see if I can write down the correct thing. So let's see. So I'm going to just stick with the notation that I had before on these slides, just so that I don't get too confused. So I'm going to work with the topos Y and an object U, and I think I was calling the geometric morphism P.
Great.
And so let me just see if I can remind myself what the formula says. So remember that this P lower star has a left adjoint, which is P upper star, and it has a further left adjoint, which is P lower shriek. And the relationship is between P lower shriek and P upper star. So it's that, oh man, I hope I can do this. So P lower shriek of P upper star. I'm just going to give these things names at random. So A. No, wait, do I need to say P upper star down here too, Peter?
Yeah, so it's P lower shriek of, all in parentheses, P upper star of X crossed over P upper star of Y with Z end parentheses.
Good. That's what I thought. All right, and so then that means that this is the same thing as A cross over B with P lower shriek of C. Is that right?
Yeah.
Oh wait, it's not showing up on the screen for some reason.
Yeah.
Oh.
Oh, shoot. Sorry. Maybe this is our indication that we spent too long on this. Aaron, would it be okay with you if we came back to this?
Oh yeah, that's totally fine. I appreciate even just that pointer of
yeah. So it's
that hint of
6.3.5 of higher topos theory.
Yeah, 6.3.5.11, and I wrote a link that brings you to exactly there in the PDF in the chat.
Great.
Yeah, I just opened that. Thank you.
Peter, do you write those links manually, or do you have a way of finding the anchor?
So yeah, well, it's pretty easy. so maybe there, I'm not sure if you're referring to just like when I write this sort of link. Depending on your browser, what you can do, like if it's referenced, you can, you know, like copy the link. But I don't know, my browser used to be able to do that and now it can't. But then what the you know, what the links are essentially is always, you know, the PDF, hashtag, theorem, and then number. They're like really, they're reasonable names. And then, or like PDF hashtag section number, PDF hashtag section.
Yeah, okay, yeah, so you do it manually.
Something. Yeah,
except for the appendix to higher algebra, right?
Yeah, the appendix to higher algebra, it has to be, I think it's a theorem, like a little letter A and then theorem. But I also made a macro. So when I do citations, like in our papers, it also just creates the link, but it's based off of this sort of reasonable naming of things. So yeah, if you click on higher topos theory, higher algebra, stacks project, etc. proposition in one of our papers, then it will link you to that place in the PDF.
Yeah, I've seen that. Yeah.
And I don't do that manually. I made a smart.
Oh yeah, no, I meant you've posted links for me before.
Yeah. Oh, and also Slack now has the capability to include links within text, so you don't have to have all these long things, which is nice. Yeah. They didn't used to do that, but.
Yeah. All right. Thanks for the talk.
Yeah. Thanks a lot.
My pleasure.